So welcome to today's session of water and wastewater treatment. This is week 8 and I am here, Saptarshi Bose, PMR research scholar from IIT Madras. So as usual, we will try to solve few numerical questions as well as conceptual questions. But for today's session, it will be mostly numerical questions. So the first one is a common data question, question number 1 and question number 2. So the volume of the flocculant tank is given as 2000 meter cube of water, and there are some mixing tubes. Yes, welcome. So we will do some numerical questions today. So this is the first question. A flocculation tank contains the volume of 2000 meter cube of water, which is mixed using paddles at an average velocity gradient, that is g, of 1125 per second. Density of the water is 999.1 kg per meter cube. Temperature and the corresponding dynamic viscosity at 30 degrees centigrade is given as 0.798 into 10 to the minus 6 newtons second per meter square. So we have to calculate the theoretical power required if we want to achieve the G value as stated. So the unit will be in kilowatt. Please try to solve this as quickly as possible. Try to solve this question as quickly as possible, then we will move to the next one. If you can't remember the formula, you can refer to your notes. So we'll go for the solution. So the correct answer is 20.19 kilowatt, and this is how we'll solve. So I hope all of you are aware about this formula. This is the power required formula with respect to my dynamic viscosity, volume, and the velocity gradient. So the velocity gradient G was given as 1125 per second, and here the volume was given as 2000 meter cube of water, and mu was given as 0.798 into 10 to the minus 6. If you just put the value and calculate, you will get the answer in watt, that is 2019.93 watt. If you just convert it into kilowatt, it will be 20.1 kilowatt. So this is as easy. So the next one, this is also related to the first question, the concept. So to achieve the required G value, rectangular paddle calculators are installed. The coefficient of drag CD for the paddles are given as 1.8. The paddle of velocity was given as 0.6 meter per second, and the relative velocity which is needed for your formula, that is 0.75 of V. So this is my V, 0.6 meter per second, and from there you can calculate that is 75%, right? 0.75 of V, that is the relative velocity. This is only required in the formula. So the required paddle area you have to calculate in meter square.
Hello.
Yes.
Yes, sir. Sir, can you show me the last question again? One number. Just
Okay. The question was,
actually, I need to write down. Yes, just
uh,
hold on. Ha,
okay. Okay. No problem.
just hold on, sir. Yes, yes.
No.
Just show me answer, sir. Show me answer of this question. Okay, sir. Thank you. We can go for two numbers. Yeah. Second number question. We can go.
Maybe one more minute, then we'll go for the solution, because today we have various numerical questions to solve, so it will take some time. Okay. So the answer will be 25 meters square. This is how we'll solve. This is another representation of the power, which we already did here. The same thing we are calculating with respect to the actual population tank. This is my coefficient of drag. This is my area, right? Area of the paddles, then the row density I'm getting, and this is the relative velocity. So this is the formula. I hope you all of you are aware of this formula. When you will go through the notes, you will find this formula. This is also related. P can be also transferred into this. So that was my previous one. So P can be wrote as P can be written as mu v g square in this format, and also in this you can take care of this coefficient of drag area of the paddles through the density and the relative velocity. So you need to calculate this A. So I'm writing A equals to 2P divided by CD A rho EP cube, and here 2 multiplied by my P, and this power we already calculated P as 2019.93 watt. So I'm writing 2019 here, 2 multiplied by 2019, right? And from the previous question or the previous answer, I got this P value. Then coefficient of drag was given as 1.8, and this rho was given at 999.1, and TP was calculated. This is 75% of this 0.6 meter per second, right? So 0.75 multiplied by zero point 0.6 cube, and I'm getting area as 24.65 meters square. I hope this one is clear, and we will go for the next one. This is a theoretical question, the conceptual question. So two statements are given. You have to say whether they are correct, both, or some one is true, another one is false, something like that. Okay, the solution correct answer is D.
Option 2.
Okay. So you are saying option 2, that is B, but the correct one is D. Large frogs are easily removed in the settling tank. Yes, if the frogs are large, then it can be easily removed. And then it is advantageous to vary the G value, right, over the length of the population basin. So what happens is G and T, two factors are there. This is the time, and this is my G value. So suppose this G value is higher and T value is lower in the first half, and suppose I am dividing the tank into two halves. Suppose here G value is higher, the first one, T, the time is low, and in this place G value is lower and T is more, the time is more. Then what will happen? It will increase the collision in the first phase, and it will produce the small dense blocks, right? So the volume will be small, but the density will be higher because the time is less. We are giving them, providing them very less time, and we will very higher velocity, then it will form some dense flux rate. But in the second half, what will happen? Then we are giving the more time and we are reducing the G value. Then this small dense flux will form bigger flux. All the small flux will try to form a bigger flux because time is more here and this velocity is a little bit slower. So it will settle at the end with a large and also dense flux. So the next one in the perikinetic population mechanism, which of the following phenomenon is responsible for the contact between colloidal particles?
Option A.
No, sorry, the correct answer is the Brownian motion because of the collision of the colloidal particles. We get this mechanism. So the next one is another numerical question. Again, common data for question number 5 and 6. Please write down all data. A sedimentation chamber of dimensions are given 12 cross 1.5 cross 0.8. So that liquid depth is 0.8 rect and the flow is given as 720 meter cube per hour. You have to calculate surface overflow rate in the required unit, meter cube per hour per meter square.
Answer is 40 meter cube per meter square per hour.
Okay. Okay. So we will check. Yes, you are correct. Congratulations. Like 40 meter cube per hour per meter square. For others, I will just explain quickly that surface overflow rate. I discussed this type of questions many times, numerous times during past sessions. So nothing new to say. So this was my flow rate 720 meter cube per hour, and we'll go for this top surface area, right? So if this is my tank, in top surface area, I will calculate. So this is 12, and this side is 1.5 meter. So I am dividing this area with the flow rate, whatever flow is coming, that is 720 divided by 12 multiplied by 1.5. I am getting 40 meter cube per hour per meter. So the next question is the detention time.
Sir, show me question. Show me question.
Same question.
One point two minutes.
Okay. So the correct answer is yes. Thank you again. 1.2 minutes. So the detention time is very easy. That is nothing but the volume divided by my flow rate, and volume was 12 multiplied by 1.5 multiplied by 0.8. That's my tank volume. That's my tank volume divided by 720. 720 is my flow rate. So this is my 720 flow rate. I'm getting 0.02 hours. That is not practical. So the next one, again conceptual question. Type 3 settling involves flocculating particles in the dilute suspension. The next one is Stokes' law cannot be used to determine the terminal velocity of flocculating particles as they continually change their size and shape. We will go for the solution. So the correct is B. That is statement 1 is false and statement 2 is true. Because in Stokes' law, if the flocculent particles are increasing, right? So if the flocculent particles are changing, like this was the first time the particle, then it's changing, is getting bigger, bigger. So it's actually changing size as well as shapes. It might be in a different shape. So that's why Stokes' law cannot be used to determine the terminal velocity of flocculating particles. And the type, in case of type 3, this is not in dilute suspension. It is like a thick blanket. It is coming down. So like three thick blanket, all the particles are here. So this is, suppose this is my measuring column. So the first, this is my type 4, this is my type 3, it is coming as a blanket, and this is the diluted or type 1. So this is not type 3, it should be the type 1, right? In case of dilute suspension. Again, conceptual question related to the flocculation involves the compression of double charge layer present on the surface of the collided particles. So the correct answer is C here. The statement 2 and 3 are correct.
Option D.
C. The correct answer is C. Only 2 and 3 are correct statements. So in case of flocculation, this is not in case of flocculation, this is in case of coagulation. So please be careful with the difference between coagulation and flocculation. So in case of coagulation, the compression of double charge layer present on the surface of the colloidal particles happens, and the compression happens, the compression of the two particles with double charge. Maybe the first layer is negative, then positive, negative, and this is also having the same characteristics. So these are coming towards each other. So that's why this double layer is getting compressed. It is getting reduced, right? So this is the fundamental concept of my. Now see the double layers are getting compressed. Suppose this is the thing. They are coming closer to each other, something like that. So this compression is related to the coagulation, not the flocculation. So please be careful. And the population process involves the agglomeration of destabilized particles. Yes, because if they are not destabilized, they will have this layer. So we are trying to destabilize these particles to break this charge stabilization. That time they will come closer to each other, and then the van der Waals force can act. And the second one is cationic polyelectrolyte can be used as both coagulant and the flocculant. So the next one is conceptual question, not a numerical question. I already discussed I already discussed the concept behind this question few minutes ago. So anyone wants to answer? I already discussed the concept behind this question just few minutes ago. Okay, the correct answer is A. C, I already told you. If you just divide the, suppose this is my rapid mixing tank and this is my calculator basin, right? So I will keep G value higher and residence time lower for this first phase, and then G value lower and T value higher for the next phase. So this is my rapid mixing basin and this is my calculator basin. So here G value is higher, T value is less. So the dense smaller flux will form, and here the large and those small dense flux will come closer to each other and will produce larger flux due to lesser velocity gradient as well as higher residence time. So this B1 and P, and then A is connected to these two and Q. So the next question is a numerical type question. Already discussed similar questions in today's session. The Q influent is given as 12,960 meter cube per day. Dynamic viscosity of water is given as 10 to the power minus 3 Newton second per meter square. Velocity gradient of rapid mixing tank is given as 850 second inverse. The tank is used to blend 35 mg per liter of alum with the flow for a detention period of 2 minutes. So you have to find out what is the power input required for the mixing. Okay, we'll go for the solution. So the correct answer is around 13 kilowatt. The same formula I am using here, E equals to G square mu V. So mu was given as the dynamic viscosity of water, 10 to the power minus 3 Newton second per meter square. G, the velocity gradient is 850 second inverse. So first we need to calculate the volume because it was not given. The flow rate was given, 12,960 meter cube per day. First convert it into meter cube per second because it will be easier. So I am just converting it from day to second, dividing by 24 multiplied by 60 multiplied by 60. So the volume is 0.15. This is my flow rate multiplied by my retention time, that is 2 minutes. If you convert 2 minutes into seconds, it will be 120 seconds, right? So I'm writing this 0.15 multiplied by 120. I'm getting the volume as 18 meter cube. So just put the values here, 850 square, 10 to the power minus 3, and multiplied by 18. This is my new value. I'm getting 13,000.05 watts, and it can be converted. So the next one, a water treatment plant has a flow rate of 504 meter cube per hour. The particle of certain size, the particle has the settling velocity of 0.14 centimeter per second, and the required plan area you have to calculate for type 1 settling tank, and this should remove 90% of the particles. of that size. Suppose it has a certain size which has the settling velocity of 0.14 centimeter per second. So basically you have to calculate the plan area of the settling tank. This is a easy question, but little bit tricky. You have to think. That's it. But it's very easy. Like nothing is there. So the next we'll go for the solution. The answer is 90 meters square. Here flow rate I am getting as 504 meter cube per hour. You can convert it to meter cube per second. I already discussed how to convert. So the velocity or the settling velocity, sorry, it is given as 0.14 centimeter per second, right? So again convert it into meter per second, 0.0014 meter per second I am getting. This is my settling velocity. This is my flow rate. So the plane area will be Q divided by Vs, right? That is 0.14 divided by 0.0014. That is 100 meters square, right? And this is for 100% particles removal. If we are considering 100 particles removal, so you know, I think all of you are aware of this fact that the surface area of the tank will determine the particle removals, right? That's why we are always calculating SOR, surface overflow rate. So this area will determine how many particles can be removed, or this area will determine, right? This is the concept behind this. So this is, you can say, this is a proportional. These two uh, these two factors or the parameters have proportional relationship. First one is the plane area. Suppose this is my plane area and this is my removal percentage. So if the plane area is increasing, removal percentage is increasing. If the plane area is increasing, removal percentage is increasing. Suppose this is my 100 meters square, right? 100 meters square, this one. For this I am getting 100% removal. This is 100% removal I am getting. This is 0 from 0 to 100. Now I need 90% removal, not 100% removal. So it will be lesser value, right? It will be lesser than this. I hope now this is visible properly. So this value I'm getting, so this will be lesser than this 100 meters square. As this is in a proportional relationship, so we can write at 100 multiplied by 0.9, 90% I need, so that is 90 meters square. The next question, common data question for 12 and 13. Consider an ideal horizontal settling basin having depth of 3 meters. I'm getting Q influent or the flow rate is 9,600 meter cube per day. Settling time 7.5 hours. T is 20 degrees centigrade. Mu 10 to the power minus 3 kg per meter second. Rho is 1000 kg per meter cube. Now you have to assume the laminar flow conditions. The settling velocity in meter cube per meter square per day. You have to calculate. For question number 3. Okay, we will check the solution. So the answer is 9.6 meter cube per meter square per day, right? So the settling basin detention time was given as 7.5 hours, right? So I'm converting these into seconds. 7.5 multiplied by 3,600. I'm getting 27,000 seconds. And then the surface overflow rate. Sorry, the settling velocity we are getting as depth of the tank divided by the settling time, right? So this way I am getting the settling velocity. Suppose this is my tank. So this is my depth, right? This is my depth, 3. Depth of the tank is 3 meter, right? So suppose some particles is coming here at that position. So it will take how much time to go down? But actually it will go down like that. But this is my velocity. So the settling velocity here, I will check how much time it will take to go down from this place to this place. So this is my depth, and it is having the settling time as 27,000. So I'm dividing this depth with depth in meter divided by second. I'm getting 1.1 into 10 to the minus 4 meter per second. If you convert it into meter cube per meter square per day, I'm getting this much, 9.6 meter cube per meter square per day. Right? So we'll go to the next one. Now consider the spherical sand particles having diameter of 0.01 mm and the specific gravity as 2.65. The percentage removal of such sand particles in the settling tank. You need to calculate. Okay, so the answer is 76.5%. The settling velocity of the sand particle can be calculated by using the Stokes law under the laminar condition. We are considering this because nothing was written in the question, so we can consider this as a laminar condition. So the Vs is equals to rho g multiplied by g minus 1 d square divided with 18 mu. Now you just have to put the values. Diameter was given as 0.01 mm. It can be written as 0.01 into 10 to the power minus 3 meter. Then g was 9.818 meter per second. Then this capital G value or my the specific gravity was given as 2.65. Rho is 1000 kg per meter cubed for water and mu is 10 to the power minus 3 kg per meter second. Just put the values here in this equation and you will get this, right? The 1000 multiplied 9.8, 2.65 minus 1. So this is my mu, right? This is my D. I'm getting 8.415 into 10 to the power minus 5 meter per second. This is my actual settling velocity of that particle if I test with respect to the Stokes law. So it will take 8.415 into 10 to the power minus 5 meter per second. But here we are giving how much velocity we are giving, providing 1.1 into 10 to the power minus 4. This velocity is 1.1 into 10 to the power minus 4. We got this velocity from the previous question, last question, right? So be careful with this concept because this is concept should be clear. So this velocity is required to touch these sand particles to the bottom of the flocculent tank, right? This is my flocculent tank suppose sand particles to get down. But the and we are also providing this velocity, right? What is flowing like that. So if this velocity is more than this one, right? More than this one, then we will get 100% removal, right? So the flow velocity, if the flow velocity is more than this settling velocity, if the flow velocity suppose is more than this settling velocity, then what will happen? We will get lesser percentage of removal, right? Not 100%. Sorry, this one will be lesser percentage if this flow velocity is higher. So particle will not get enough chance to get to reach at the bottom surface. All the particles will not get enough chance or enough time because this flow velocity is higher with respect to my settling velocity. But suppose this settling velocity is more, if SD is more, and with respect to flow velocity, then we can get higher percentage of removal. Right? So that's what we are checking here. This is my the flow velocity we can say, and this is my Stokes according to Stokes law. That much of time will take to reach down. So I'm getting 76.5%. So that much of particles can be removed. Actually, I'm getting this velocity from how much depth is there and how much detention time I'm providing. So I'm getting this velocity. The next one is consider a flow evolution treatment plant. Alarm dose is given as 25 mg per liter. Flow is 0.3125 meter cube per second. Influent suspended solid concentration 32 mg per liter. Effluent suspended solid concentration 17 mg per liter. Now the alarm stoichiometry equation is given as this one. So the amount of total dry sludge solids produced per day you have to calculate. What is the amount of total dry sludge solids produced per day in kg per day? That will be the unit. Okay. We check the solution. So the flow rate was given as 312 meter cube per second. That can be converted into 27,000 meter cube per day. Alarm added was dose was 25 mg per liter. Now from the equation, you can see that from the equation, For one equivalent of alum, I'm getting two equivalents of ALOH whole 3, right? So, or better to say, we can also say like that for 1 mole of alum produces 2 moles of ALOH whole 3. I already discussed similar concept in last session that I can remember. So 1 mole of alum produces 2 moles of ALOH whole 3 aluminum hydroxide, and then I am getting molecular weight of these alum as 594 gram. You can calculate easily. And the molecular weight of ALOH whole 3 is 78 gram. So I'm getting it is as simple as some unitary method which we are doing since our class 6 or 7 standard. So 574 94 gram of alum produces 2 into 17 8 gram of ALOH whole 3. That will precipitate as a solid sludge, right? So here for one, this is 1 mole, this is 1 mole, producing 2 moles of ALOH whole 3. So one molecular formula I am getting 1 mole, 594 gram of alum produces 2, that is 2 multiplied with 78 gram of ALOH whole 3. That will sorry, precipitate as solid. Then 1 gram of alum produces simple unitary method 2 into 78 divided by 594. I am getting 0.263 gram of ALOH whole 3. That will precipitate. So now 20 mg per liter of alum will produce 25 multiplied by 0.263, same unitary method, mg per liter of solid sludge. And you can convert, we are getting this 6.575 mg per liter of solid sludge, right? Because this was my alum dose. So if 1 gram is producing that much, so 20 mg per liter will produce how much? That is the thing. And the suspended solids removed, it was initially 32 influent and effluent 17, so removed 15 mg per liter. So this will also precipitate with the flux, right? So not only the ALOH whole 3, it will also contains my suspended solids. So I'm getting 25.26 mg per liter. If you add these two, I'm getting 21.575 gram per meter cube. Just convert the units, you will get that. Now the dry sludge solids removed per day. This is my flow rate multiplied by my solids removed. The flow rate is 27,000 meter cube per day, and for every meter cube of water, I am getting how much sludge? 21.575. So if you just multiply meter cube protein cancelled, convert this gram into kg, I am getting 582.52 kg per day. The next one, the flocculation chamber is equipped with 10-meter long, 0.32-meter wide paddles. Both paddles are supported parallel to the horizontal shaft. The shaft rotation speed is 3.5 rpm. Center line of the paddle from the shaft is 1.75 meter. Coefficient of drag is CD is 1.8. The ratio of the velocity of the paddle with respect to water to the velocity of the paddle. Fixed coordinate, that is k value is given as 0.75. So you have to calculate what is the power consumption by the shaft in watt. A similar question I solved today, little bit different but almost similar. Okay, so the solution will be something like that. it will be 640.2 watt. So the power given, this is my formula. Please go through the notes, the lectures. You will find power as 1.2 CD, coefficient of that rho W multiplied by AP and Vp cube, right? So Vp is my velocity of paddle with respect to the water. So I will calculate this? This is K multiplied by 2 pi Rn, and here K value or the velocity ratio of velocity of paddles with respect to water velocity is given as 0.75, right? And here the shaft rotation speed was N was given as 3.5 RPM, right? So just put the values here, the N value, K value, and how much this this center line of the paddles from the shaft I'm getting as 1.75 meter, right? So this is my distance from the center line of the paddles from the shaft is 1.75 meter. So I am putting this 1.75 here. This is my distance. It is my rotation. It is converted into seconds. It was in RPM, right? So rotation per second, that is 3.5 divided by 60. I'm getting a 0.4808 meter per second, right? So this is the velocity of paddle with respect to the water. So area, you can calculate the area of the paddles, and I'm getting here, that is, it was 10-meter long and 0.32-meter wide paddles. So 10-meter long, 10 into 0.32 is my length, that is my width, and this is 3.2 meter square area. So here, half 1.8 into 1000 into this 2 multiplied by 3.2, because paddle will have two surface area, this one and the back side, top side and the back side, top side and also back side. Right? So that's why 2 multiplied into 3.2, and this is my VB. I'm getting 640 watt, right? So thank you for joining today's session. Now we'll end here. Hope you enjoyed.
Thank you so much, sir.
Thank, thank
Thank
you.
you.
So we'll meet in the next session.